Okay, we got a wonderful loaf of bread. Assume I wanted to find the volume of that loaf of bread. Well, first I'd have to assume it's a uniform loaf, and obviously a real loaf of bread is not completely uniform. I'd also have to be able to make each slice exactly the same, and of course these aren't all going to be exactly the same. But if it was a perfectly uniform loaf of bread, and I can make perfectly identical slices, if I can find the volume of one slice, I can then multiply by the number of slices. All right, so let's harvest some wheat. Let's make some bread. Either that or we'll do some calculus. Okay, so basic setup is that I have to take a look at whatever solid I'm going to work with. So maybe it's a sphere, maybe it's a cylinder, maybe it's a cone, maybe it's a rectangular prism. That's going to be the first example we actually do here. And then if a picture is not provided, I highly recommend you draw a picture. And then of course we've got to figure out the formula for the area of the cross section. Right, so if you think about a slice of bread, that'd be kind of like if you're like, oh, I got a slice of bread, I want to butter it. Think about the area you try to apply the butter to. Then we're going to integrate the area formula over the appropriate interval to get the volume. You're going to think, wait a minute, how does area become volume? Hang on for just a moment. So here's the first question. Let's try to find the volume of a rectangular prism with a length of 12, width of 4, and height of 8, all those in centimeters. Now I know what you're probably doing. You're probably cheating. You're probably grabbing a calculator, doing 12 times 4 times 8 and getting an answer. Well, if you did that, just kind of put that answer off to the side, and when we're done with the calculus, we'll see if we get the correct answer. All right, so there's a pretty picture. A 4 by 8 by 12 rectangular prism. You'll notice I'm going to orientate it so it appears that the x-axis goes along that length of 12 centimeters. The y-axis goes along that height of 8 centimeters. Now, if I can imagine slicing this prism up, and my artistic abilities are really failing me here, but try to get it so it looks like I've sliced it and do a bunch of equal slices. And again, for this to really work, we need to get those slices very, 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 very thin. So thin that the thickness is almost 0, right? So the thickness is going to be delta x, right, dx. And of course, the area of each slice is 8 by 4, right? 8 times 4 is 32. So that's the precise area. If you think about like if you had slices of bread and you're going to try to butter them, that would be the area you're attempting to butter. And so we're going to take that area formula and we're going to integrate to get the volume. Again, if you're wondering, well, just a minute, how does area automatically become volume? Well, remember the thickness of each slice is delta x, or dx. So if the area is 32, and I multiply it by the thickness, dx, all of a sudden I got volume, right? Area of the base times the height, that gets me volume. So the volume of each one of those little slices, very thin slices, is 32 dx. So if I integrate, now again, I'm going to start at 0, right? I've got that rectangle lined up, so that's at 0. And for x, I got to go up to 12, right? I'm going to go from left to right. So what is the integral from 0 to 12 of 32 dx? Well, if I integrate 32, I get 32x. And then, of course, instead of plus c, I say, no, it's a definite integral. I've got to plug and chug. So I got to do 32 times 12, subtract 32 times 0. And amazingly, we get 384. Is that what you got when you did the math originally? Probably. Oh, and it's not square units, it's cubic units. Although I should have put cubic centimeters, huh? I kind of goofed that one up. You know what? If every slice is exactly the same, though, We could have just done geometry. We didn't really need calculus. So if every slice is the same, so we gotta jazz it up. I can't believe I put cubic units there instead of cubic centimeters. We'll get that fixed. So let's do a square pyramid instead, where the base is a square, side length is 20, so it's a 20 by 20 square for the base. The height is 60 feet. So this way, even though each slice is still going to be a square, each slice is going to be a slightly different size, right? I mean, at the very bottom, you got 20 by 20, that's 400 square feet. But then as you move up, well, they get smaller. So I've got a picture of my pyramid there, and just a minute here, that doesn't look like the height is 60. It looks like someone knocked it over on its side. Why would I do something like that? Oh, think about the slices I want to make. I want to make square slices, and you can kind of see one of the slices contained within that pyramid there. And then when I add them all up, when I do the integration, I want the x-axis to go along with the dx. And notice that unlike the previous example here, try to get the picture, or I stole a picture off the internet, where you can see that the x-axis goes from the apex of the pyramid, or that vertex, I guess you would call that a vertex on the pyramid, through the center of the base. All right, so that base again is going to be a 20 by 20 square, and the height is 60. So when we integrate, we're going to integrate from x equals 0 to x equals 60. So what is going to be the area of any given square slice, right? Not the base. I know the base is 20 by 20. But if I just grab one of the slices from somewhere inside that pyramid, what is the area of that slice? Well, the side length S is going to compare to 20 the same way that distance x compares to 60. Sounds to me like we got to set up a proportion and solve for S. Now, as long as I'm consistent, I can set up the proportion about any way I want. So I'm going to put S over X and then 20 over 60. If instead you wanted to put S over 20, you could have put S over 20, but then you'd have to put X over 60. Right? You got to be consistent with your comparison. So I can say, hey, S compares to X the same way 20 compares to 60. Or I could have said, hey, S compares to 20 the same way X compares to 60. Let's see, let's multiply both sides by X. Oh, nope, before I do that, I reduced. 20 over 60 reduces to 1/3. Multiply both sides by X. So the area of any one of those, not the area, I'm sorry, the side length S, it must be a long Monday morning here or something. The side length S is going to be 1/3 times X. So the area of any given slice, well, I know the area of a square is just S squared, right? If I know the length of the side, I just square it and I get the area of the square. So I need 1/3 X times another 1/3 X. Well, 1 times 1 is 1. 3 times 3 is 9. X times X is X squared. That is the area of any one given slice. Now again, how does this become volume? Well, remember, each slice has a thickness, right? The thickness of dx, the tiny little bit that I'm moving. So let's add them up, right? I've got to go make some room first, I guess. I need to go 0 to 60. I'm going to cut up in a bunch of thin little slices, and the area of each of those thin little slices, the surface area, or well, the surface of one side there, 1/9 x squared, and it becomes volume when I consider the thickness. I love how in math they always call that the area of the slice, or area of the surface. I think of these as being three-dimensional objects, and I think, hey, it's really just area of the base times the height for volume. Where what they call a slice, I think it was being a base, but anyway. So I got 1/9 x squared. Let's integrate that. Well, I add 1 to the exponent, so the new exponent's 3. So I got to divide by the new exponent. Well, if I divide by 3, instead of 1/9, I now have 1/27. We evaluate it at 60 and 0. Of course, 6 times 6 times 6 is 216. But oops, that's not a 6, that's a 60. So I better slap 3 zeros on there. Huh? And either you said, well, no, I want to factor out that 60 and do some cross canceling, or you say, no, I'll just multiply it out this way, then grab a calculator. And it actually comes out quite nicely, just 8,000. And of course, I should have put 8,000 cubic feet because I did the example in feet. But I was so excited that we're doing cubic units that instead of cubic feet, I put cubic units again. But go figure, right? So let this rule run in your head for like a couple days, and next lesson we'll try to get another example up. Let's see if I can talk through it without getting overly tongue-tied, and maybe you can get the labels correct. And then maybe after talking you through another example, maybe we'll give you one question to try and do. But the trick with volume here is that we want to be able to slice it so each slice is the same shape. Today we made each slice a square because we can find the area of a square, or the previous example it was a rectangle. Rectangle is length times width. And then we just do some slicing and figure out the area of each slice. And then with the magic of integration, because the dx area becomes volume. And then with the integration, we add up all those volumes and we get the total volume.